Shao for his second lecture on the generations of rational maps. Yeah.
Let's. So I hope I won't degenerate as much as the French team yesterday.
Whoa.
And so since we have an expected guest, so I'm going to do a small recap from what I did 2 days ago. So I was interested in dynamics of a rational map of degree at least 2 over a strange field. So K is a complete non-Acmean field, algebraically closed. So NA is for non-Acmean field. And so I explained that it was better to look at the action of F on the Berkovich analytic space. That was the Berkovich analytification. Which was an R3. In this space, we had a lot of interesting points associated to balls. So I denoted like this, zeta AR. So what is AA is an element in K. R is a non-negative real number. And so this is a point associated with the ball, closed ball of center A and radius R. And so I defined the Julia set in a weird way. So first what I did was to define the equilibrium measure, denoted by mu of F. So F is a finite map on this compact space. And so you can define the pullback on probability measures. So if you take X, any point in the Berkovich identification of this form with R positive, then you can show that if you're pulling back this measure, you get a positive measure of mass d to the n. So by normalizing, you get a sequence of probability measures. And I check that this converges at least when X is a special point as such the closed unit ball, okay, the Gauss point. Now this converges to measure. So in fact, you can extend the argument to show that for any such point, the sequence of pullback measures is going to converge to actually the same measure. And the Julia set will be the support of this measure. And I didn't say, so mu F is mixing, in particular is ergodic. Okay, and then I looked at 2 examples of quadratic polynomials, so z squared plus t, and then d squared plus 1 over t. So in that case, something strange happens, is that the Julia set is reduced to just 1 point, which is this Gauss point. In that case, so the Julia set is more complicated, is a counter set. So I didn't explain, but in fact, this lies inside the set of classical points. And the topological entropy is positive in that case. Your map is actually conjugated to the shift on 2 symbols. Okay. So I wanted to first look at the third example of the Macmillan's family. So yeah, so there are many. Okay, so let me look at this family now, z squared plus t over z cubed. So the computation I'm going to make are not specific to 2 and 3. You can replace by any integer at least greater or equal to 2. But when you choose z squared plus t over z squared, something different happens. So this is why I choose here 3 and not 2. Anyway, so okay, so this is a family of rational map of degree 5. And so I explained last time that you can look at its non-Archimedean limit, so which is a rational map over some field. So the field I'm going to consider, so you can consider first is the field of formal Power series, Laurent series, sorry. But the point is that this field, so with its t-adic norm, so this field is nice, it's complete, but it's not algebraically closed. And I usually prefer with working with algebraically closed fields. And so you need to first take its algebraic closure, which is the field of Puiseux series. Unfortunately, it's not complete, so you complete it, and then you get this field L. But in practice, you can always think L as being the field of Puiseux series if you want. Okay, so now my goal is to try to compute the Julia set of this map. And so we do as in the previous examples. So we look at the line, the geodesic, if you want, joining 0 to infinity. So what is the point in here? This is a point attached to the ball of center 0 and radius r. And so here what you can see is that 0 is mapped to infinity and infinity is mapped to itself. And so you can check easily that in fact this whole geodesic is mapped into itself. So let's compute its the restriction of f to this geodesic. Okay, so how you do that? So you want to compute, you pick any r, and you want to compute these things. So the way you do that is that you take any element in K whose norm is R. So suppose R is in the value group of this of L. And then you try to compute the norm of its image by F. Okay, so here what you see is that if Z is small, its norm is small, then so this guy is going to be small also. But this guy, when you divide by 1 over z cubed, it's going to be very big. So the norm is going to, so the term that's going to win is this one. And when the norm of z is very big, then conversely, this is the one that's going to win. And so there is a critical parameter when the norm of z to the square is precisely equal to the norm of t divided by the norm of z to the cube. Okay, and so by convention, I'm going to assume that the norm of t is 1 over e. And so the critical value is when, let's say, when the norm of z to the fifth is equal to the norm of t. And so norm d is e to the exponential minus 1/5. Okay. So you have then two cases. So if r is less or equal to exponential minus 1/5, or r is greater or equal to this. So when it's less or equal to, then I explain that this is a term who's winning. So you get the point attached to the ball of center 0 and radius r minus 3 divided by e. And here you get this. Okay. Yes, yes. Okay, so now, okay, this is a nice formula. Sorry?
And compute here. So when z is 0, you go to infinity, right?
Yeah.
So when you go here to 0, you're mapping to infinity.
Okay. So the ball, yeah.
I'm not saying, be careful.
The ball which is
I'm cheating a little bit. I'm not saying that the ball centered at 0 is mapped to a ball centered at 0, because 0 is mapped to infinity. But yeah, in practice, what you do is that you have to think that the point z that you choose are not in the direction of 0 and infinity. And you compute, you pick any point like this, and you compute the norm of its image. Okay, and when you do that, this gives you these formulas.
Yeah, you're right.
Sure, can you take it? Mine shows the norm of t to be 1 over e.
This is my convention. You don't like my convention? Okay, so you want this to be strictly less than 1. This is something which is fixed. And why not? Okay, usually I explained last time that this t-adic norm is exponential minus a valuation. And well, the valuation is the order of vanishing of your Power series at 0. So yeah, you get this. Yeah. If you don't like this, take 1 over pi, you know, over 2. Okay, so so here what you see is that it's probably more convenient to look at the action of this map on the set of radii, but on the log of the radii, because here you get r mapped to r minus 3, here r goes to r to the square. So if you want to see something like piecewise linear, it's better to work with the log of r. Okay, so this is 0.0. So I said that there is an import parameter which is minus 1/5. Okay. So the 0.0 corresponds to the radius 1, and the zeta 0, 1 is mapped to itself. Okay. So we have that point here. And then if you look in log coordinates, above minus 1/5, the slope is 2. Okay, so you do something like this with slope 2. And then at this parameter, then the slope here is going to be minus 3. Okay, so yeah, so something like this. Okay, so in log coordinates, the map looks like this. And so now, so where are these? What is this point? This point is minus 1/3. So it's just easy computations. And so what you can do is look at the square here. So you can restrict your map to the segment between minus 1/3 and 0. Okay, so what you see is that, so this segment on the first open segment here, let's call it I0, this I1, and the whole segment, let me call it I. Then here your map is is affine with slope of minus 3, and then on this segment I1 is also affine with slope 2. So if you restrict, so here I'm making some kind of identification. I'm identifying a point in the segment with its image. So if S is in I, I'm going to identify this with the point zeta 0 exponential x, right? So what you see, so let me do a small zoom if you want. So if you restrict, so this is 0, this is minus 1/3. So I didn't compute the numbers, but so this parameter here is minus 1/6, so minus 1/5, and there is another one that you can compute also. Whoops. So here's slope 2, here's slope minus 3. Okay? Okay, so now what I'm going to show is, in fact, the Julia set is included in this segment. So this is not completely clear because I computed only the map on this one geodesic between 0 and infinity, which is very small inside the Berkovich space. But the observation is like this. So if you pick x in I can compute its pullback, the pullback of the direct mass at x. And the formula says that, okay, well, this is the sum. This is a sum of direct masses at all preimages of x with a weight which is exactly the local degree at the preimage. So here, if so, the observation that here is that the map, the restriction of f to I0 and I1 are bijective map onto I. And so my point x has at least one preimage inside I0 and one inside I1. So let's call it delta x0 and delta x1. And now I need to compute the local degree. And so I need to relate this to what you see on the blackboard. In fact, the thing is that the local degree is given exactly by the slope. So here it's 3, and here it's 2. Okay, plus maybe some extra terms. But then remember that the degree of f is 5. And when you pull back a probability measure, you get a measure of mass 5. And so here you already have 3 plus 2 is already 5. So you don't have anything else. Okay? Okay, so in other words, so the pre-image of the segment is so f minus 1 of I is I naught union I1, and it sits inside I. Okay, so now by definition of the Julia set, so if you start with your preferred point, maybe 0, so this corresponds to the Gauss point, you start pulling it back, then you know that it's going to be a sequence of Dirac masses supported inside I. So this implies that the Julia set actually sits inside this segment. Okay? Okay, but we can do a little bit better. So what is exactly this Julia set? In fact, this is a set of points in I such that their whole orbit stays in I. So it's the intersection for I over all positive integers of f minus n of I. And this is, so you have a canonical map. Again, let's say we can look at maps from this set to 0, 1 to the n that record the itinerary of your points, of the orbit of your points inside the segment. So how do you define this? So if you take a point in the Julia set, let's say x, so what is epsilon of x? So this is a sequence, epsilon 0, epsilon 1, etc., such that fn of x belongs to one of these two intervals, so I index epsilon n. Okay, and since the map here is expanding, so it has slope 3 and 2, you can show that this is actually a conjugacy. So again, so in particular, J of f is a counterset, and again, the topological entropy is positive and equal to so the shift. Sorry, I didn't say here what is the map, but this is a shift on the set of symbols. And this is a full shift. And so the topological entropy is the topological entropy of that guy, which is log 2. Okay? Okay. So one remark that you can also compute, in this case, the metric entropy of the measure. It's completely explicit. And so it's a product measure, but beware, it's a measure that puts a mass 3/5 on the interval I0 and 2/5 on the interval I1. And so if you compute the metric entropy, you get something which is strictly less than log 2. So the equilibrium measure in this case is not the one of maximal entropy. Okay, it's not. It's just an observation. And I want to, since my aim is to discuss Macmillan's rigidity, I would like also to look at the multipliers. So of which point? So let me take a classical point in P1 over L. And let me assume that this is fixed, or maybe a periodic of some period. Okay, so how do you compute these points? Well, you look at the, let's say for p is equal to 1, you are just looking at the equation z squared plus t over zq is equal to z. And this has solutions Okay, maybe not inside the field of Lorentz series, but at least in the field of Puiseux series. Okay, and then you can look at its multiplier. So what is, let's say, mu of C. So what is the multiplier? Well, you look at the differential of f and h, the p, and you compute at z. And again, so what you get now is an element in the field of Puiseux series. Okay. So what is the observation here is that, so there is a general fact, which is a generalization of what we know over the complex, is that if you take a periodic point like this, and if you suppose that the norm of the multiplier is bigger than 1, so that the point is repelling, then in fact Z belongs to the Julia set. Okay? But here there's something strange, is that we check that the Julia set is inside a segment in the middle of the Berkovich space. And so it cannot contain any endpoints. And a point like this is identified to its ball center Z and radius 0. So it's an endpoint inside your R3. Okay, so a consequence of this remark is that for this example, the Macmillan family, F and A has no repelling periodic, let me insist, classical points. Okay. Yeah. Okay, so all points are either attracting, like infinity, or indifferent. Okay, so now this is all I wanted to say about these examples, and now I would like to state two results on the dynamics of a general rational map over a non-Euclidean field. So the first one is a characterization of those rational map for which the Julia set is reduced to 1 point. Okay, so this is my first theorem. So K is a non-Archimedean complete, algebraically closed field. And F is a rational map of degree D at least 2. Then the following are equivalent. Okay, so first, the equilibrium measure has an atom. So the mass of some point inside the Berkovich space is positive. So the second condition is, okay, in fact, if mu f charges 1 point, then you're in the situation of d squared plus t. After a suitable change of coordinates, the measure is actually the direct mass at the Gauss point. So there exists phi inside PGL2 of K, such that the measure, equilibrium measure of phi f phi minus 1 is a delta mass at this famous point xg. Okay, the Gauss point corresponding to the unit ball. Okay, so the third thing is traduction of this, translation of this. So there exists some, projective linear transformation of K, such that the degree of the residue map, so I'm going to define this, is equal to D. And then the fourth condition, as you see, I like the entropy. So the fourth condition is that the topological entropy of F is equal to 0. Okay. So when this one of these conditions is satisfied, we say that F has potential good reduction. So good reduction means that the degree of, so I didn't define it, but I'm going to discuss this later. It's the degree of the residue map is equal to D. And if there exists a transformation such that the conjugate is like this, it's potential good reduction. Oh. Yeah, residue. So yeah, I'm going to come back to this later. So d squared plus t as good reduction. And d squared plus 1 over t or d squared plus t over z cube don't. So we check that topological entropy is positive. Okay. I cannot do anything else. To define topological entropy, you need a compact space. And so, yeah, you compute inside the brokerage space. It's the same as, okay, I'll discuss this later. Okay, so let me just spend a couple of minutes discussing this. So I was a bit quick last time. So when you have a non-Acmean field, you can look at its closed ball. And because of the non-Acmean triangle inequality, this is a ring. And in fact, it has a unique maximal ideal, which is the open ball. And so it's natural to look at its quotient, K tilde, which is called the residue field. Okay. So in the case of interest, so K is, let's say, field of formal Lorentz series. So what is K naught? This is a ring of formal power series. And what is K naught naught? This is the set of formal Lorentz series that vanish at the origin. And so the residue field in this case, whoops. So the isomorphism is like this. So you take any element in your ring here, and you evaluate at 0. You get an element in C, and this gives you a canonical isomorphism. Okay. So when you do the when you go to the algebraic closure, you don't change much because C is algebraically closed. And when you go to the completion also. Okay, so in fact, this is also true. This isomorphism is also true for K is equal to L. Okay, so what does it mean, this tilde there? So if you have a rational map, you can choose a homogeneous coordinates in P1 and write F as define F by a pair of polynomials P and Q of degree D without any common factors. And so let me call AI and Bj the coefficients of P and Q. And since you can multiply by any constant, you can always assume, can always normalize P and Q such that the maximum of the norm of AI and Bj's is equal exactly to 1. Okay, so this means in particular that they all belong to K naught. And so you can look at their images inside the residue field. And so what is F tilde? This is the rational map defined by the residue polynomials P tilde and Q tilde. Okay, so in general, you might be unlucky, and it might happen that in fact you get a constant map. Okay, so let me explain a couple of facts. So the degree of F tilde is positive, is not 0, so f tilde is not constant. This is exactly the same as saying that the Gauss point is fixed. And when it is the case, in fact, you can interpret the degree of the residue map as the local degree of f at that point. Okay, so if I come back to the condition 3, what I'm saying, so suppose phi is the identity, I'm saying that the degree of f tilde is equal to d. So let's say condition 3. With phi is equal to identity. So I'm saying degree of f tilde is equal to d. Okay. So in particular, the f of xg is equal to xg. So xg is fixed, but also the local degree hg is equal to d. And so if you pull back the Dirac mass as xg, well, you get delta at xg times the local degree, which is this number. And again, you cannot have any other thing because the mass is already equal to d. Okay, so this implies, so what did I prove? I prove that this implies 1 and 2 and 4. Okay. So before I explain how briefly how you prove such a result, I also like to come back. So last time it was maybe not super clear. So I draw this picture. So you have 0, infinity, and then you have a lot of branches. Okay, maybe not like this. I want to be consistent with my previous. So this. So I explained last time that the set of directions in fact can be almost in a canonical way related to this residue field k tilde. So you have a map from k tilde union infinity to the set of directions. So how you do that? So you pick an element in k tilde is represented by an element in k0. And you look at the direction determined by that point at xg. And if you take two elements in k0 that define the same direction, then you notice that, in fact, the distance between the two is strictly less than 1. So you get this injection. And then you also have the direction coming from infinity. And so this is a one-to-one map. So now you have two objects. So suppose that xg is fixed by your map f. I don't know, they're red, blue, and white, so you know where I'm from. So here you have f is a tree map, and so fixing xg, so it defines a map on the set of directions. So if you want, this is the derivative of f at xg, at least you may interpret it this way. And then here we also constructed this f tilde. And in fact, so under this identification, f tilde corresponds to the action on the set of directions. Okay. Okay. So now I need to come on. Yeah. Okay. So before I do the proof, or sketch the proof, I wanted to add one thing in the case of a horomorphic family. So okay, I'm a bit, so remember, so what is a horomorphic family? For me, it's a holomorphic family on the puncture disk, which is meromorphic at 0. And so I explained that you have this non-Achaemenid dynamical system, rational map, in L. And So suppose that F and A has potential good reduction. Then by condition 3 or 4, 3, it means that there exists a change of variable over this strange field L, such that the degree of the residue map is equal to D. Okay, but then you can use a little bit of algebra and in fact check that since F is defined over, not over L, but in fact over the field of formal Lorentz series, that in fact you can find a family which is defined over the field of Puiseux series. Okay, so if you replace T by T to some power, then you get in fact a family which is defined over the field of Lorentz series. And then again, same argument says, but look here, I was holomorphic. So in fact, you can check that the coefficient here are also holomorphic. Okay, so what I'm saying is that if your map here has potential good reduction, then in fact, after a holomorphic change of variable, locally near 0, then in fact, the degree of this residue map is equal to D. So, but if you compute this, this means that, Ft is P of T, Q of T. I remember that the residue field here is C, so you expect this rational map to be defined over C. What is this map? Is in fact, it's exactly F0. Okay, this is F tilde. So what are we saying here is that if you have potential good, if F and A has potential good reduction, then in fact, after a change of variable, your meromorphic family is a holomorphic family at the pole, at 0. Okay, so it's a fake degeneration field. Okay. Artin theorem. So I'm not going to say. It's because, yeah, well. It's not unique. The one that's so this is like this is not really unique. So anyway, so
what you say is that if I have potential good reduction for a family which depends holomorphically on T, then the phi
can be chosen to be holomorphic. Yeah, after base change. Okay, so what is a sketch of proof? Okay, so we checked that condition 3 is stronger than all the others. So if you start with 1, then you can use the fact that the measure is ergodic. It's going to imply that in fact your measure is supported on a periodic cycle. But then the measure of the iterate is also is equal to the equivalent measure of F. And so this cycle has to be a fixed point. So here it means that mu F is a delta mass at some point. But it's not clear that X has to resemble this point xg. And so here what you get is that, well, F of X has to be equal to X, and plus the local topological degree has to be equal to D. And then what you have to do is you need to analyze a little bit what kind of points can satisfy these two conditions. So you have the classification of the type of points on the Berkovich space. And the only point that can satisfy these two conditions are either classical points or points that resemble the xg. So this implies that X is either a classical point or X is in fact zeta A R, whoops, with A in K and R in the value group. Okay, but then this situation is not possible because for at least for some analytical reason. So this measure is in fact locally the Laplacian of a continuous function, and this is not possible that you can charge points in that are classical points. Okay, so you're back to this, and then you can look at the let's say the affine transformation. So R is in the value group. So let's say it's the norm of I don't know, an element. Let me call it a rho, and then you look at the translation, the affine transformation. Sorry, which is rho z plus a, and then it maps. Okay, I'm not. I didn't check if it's a phi of phi minus 1. That has to be like this, but okay. So in that case, phi of xg is equal to x. Okay, so if you conjugate f by either phi of phi minus 1, not sure, then you get that mu of phi f phi minus 1 is a direct mass at xg. Okay, so you get condition bar 2. Okay, so the fact that condition 2 is equivalent to condition 3 is the same computation as above. And so the only thing, so what do you check? This, and so the only thing to check now is that 4 implies the other conditions. Yeah, well, okay. I didn't check that this 3 condition implies 4. So why is it the case? It's because, so what is clear is that the topological entropy of the restriction of F to the Julia set, which is 1 point, is 0, okay? But then you need to check that you don't have complexity outside of the Julia set, and it's not completely trivial. The only way we understand this is by using the classification of periodic Fatou components. So it's interesting, we don't know this in higher dimension. So we really use the classification of periodic Fatou component. Okay, and so what about, so 4 imply the rest. So you start with this information, and then there is, so it implies by, what? Yeah, well, the metric entropy of this is equal to 0, the variational principle, yeah. That the entropy of this measure is 0, and then you need to compute, so it's Jacobian, so since the pullback of the measure is divided by d is itself, then you can use Rochlin formula that gives you some information about the local degree at the mu f generic point. So there is, let's say, some very general result from ergodic theory that tells you that the local degree in fact has to be constant equal to d at mu f almost every point. Okay, and then I see that time flies, but when you're there, you pick a point and you do pullbacks. Since the local topological degree is constant equal to d, a point has a unique preimage, and then you conclude that it has to be to charge 1 point. So blah blah blah, and you get 1. So the key is really to apply this Rochlin formula.
Does this work? Just do this.
Okay, I didn't write the proof. I thought about this long ago, and I thought I had the proof that topological entropy is 0 for endomorphisms of P2, for instance, implied that the measure has to be a direct mass at a point, but I lost my notes, so.
Local degree to the k.
I cheated here, so yeah, well. Anyway, yeah. So I think it's true, but I'm not completely. In higher dimension is at least dimension 2. You may expect that the same kind of result holds for endomorphisms of P2. So you have a notion also of a Gauss point, and that if the topological entropy is 0, then after conjugation PGL3, then you measure as to be the direct mass at the Gauss point. It's harder. It's not clear. This is how to attack this thing. Okay, theorem 2. Okay, so so remember that I had this Macmillan family, okay, for which something strange happens. The Julia set is completely contained inside the Berkowitz space. It's inside. It's contained in the segment. So I'd like to all the periodic points are indifferent or attracting, and so I'd like to characterize these maps. And so this is what I'm going to do here. So the assumptions are almost the same, except that I'm going to add the fact that the residual characteristic is equal to 0. So this is true if you don't like arithmetics. So if k is equal to L, if the residual characteristic is positive, it's no longer true. So you have to be, you really have to use these things. And then I'm saying this, but I'm not sure why I'm assuming. Okay, I don't know why I'm assuming this. Maybe it's, I think we prove this in full generality. Anyway, so forget my at least, yeah, it's safe to assume this. So assume that topological entropy is positive, otherwise you can apply the first theorem. And then the following are equivalent. So now I'm going to assume that there exists a segment inside the Berkowitz space such that the measure puts positive mass on this segment I. So the second statement is that F is special, is let's say piecewise linear, or we call it Bernoulli. So let me draw a picture. So first, the Julia set is actually included. So there exists some segments such that the Julia set is actually included in some segment I. And then you have the same picture that I described before for the Macmillan family. So this is a segment I. And you have subsegments such that the map on each subsegment is piecewise fine with some slope. Let's say so D0, D1, D2. Okay, you might not have only three a segment like this, as many as you want. But the thing is that all the DIs are at least true. So here you have a segment I0, I1, I2, etc. So the map from Ij to I is 1-to-1 with slope dj, and the sum of all the degrees sum up to the total degree d. Okay. So here I put this on purpose. So it might be the case that you have a gap. It's exactly what we saw in the Macmillan family, but you might also have no gap. Okay. So the intervals may intersect. So yeah. Okay. So in degree 4, the least degree that you can obtain with this is degree 4. Okay. In degree 4, you have a segment you split in 2. And D0 and D1 are equal to 2, and so on. So in degree 2 and degree 4, in degree 3, this kind of map cannot happen. Okay, and the third condition is that F has no repelling periodic points. Classical, right? Okay, so now I remember why I need this. So this is, okay. So this is true without any assumption. But if you want to have this, then you need the residual characteristic to be equal to 0. And this is true without any assumption on the residual characteristic. Well, anyway, you saw only one non-Archimedean field, so which is of residual characteristic 0. I mean, for now. So yeah. Okay. So I'd like to explain a little bit how this works. Aha. Yeah, maybe, okay, yeah, maybe I should give examples. Sorry. This. So what did we see? So we see the Macmillan's family. Okay, so ZD plus T over ZK, D and K at least 2. You have exactly the same picture like this with 2 intervals. One slope is D and the other, okay, I should not take D, L. One slope is L, the other one is K. So you have another example, which is, let's say, a flexible lattice maps. So remember that a lattice map is like this. So you take your favorite elliptic curve, C mod out by the lattice generated by 1 and tau. And then you pick an integer, at least 2, let's say delta. And so you can look at the multiplication by delta here. And if you mod out by minus identity, or more generally by, okay, if you mod out by minus identity, what you get is P1. And so it's this minus identity commutes with the multiplication by delta. So it defines a rational map, let's say, that depends on E and delta. And the degree of this guy is delta to the square. Okay? So now what you can do is that you can move this parameter tau. And so what you get is a holomorphic family parameterized by the space of elliptic curve, which is a puncture sphere. And you can check that, in fact, you get a rational family of rational maps of degree delta to the square and parameterized by P1. So I'm changing, when I say you have one family, in fact, depending on the parity of delta, you have 1 or 2 families, but okay. And so if delta is equal to 2, it's completely explicit. It's a so-called Schroeder family, which I wrote somewhere in my notes, and I cannot find them anymore. Where are they? So someone knows by heart. It's completely explicit of degree 4. Ah, yeah, here they are. Ft of z, 4z, 1 minus z, 1 minus t squared z over 1 minus t squared z square. And so here it's it's of degree 4 when t. No, it's not this. But I copied from Milnor, and so
To the minus 1.
This one.
1 over that.
1 over that.
Oh.
Yes.
The both have to be the distortion. It has to.
This?
Yes.
Okay. Okay, fine. So you're more knowledgeable than me. Okay, fine.
Charles, in the setting of theorem 2, does the information of the arc together with this graph determine the map?
Nope. So it's quite interesting. So so if you have a map like this, the Julia set here is completely contained inside a segment in the Berkowitz space. So if you perturb just a little bit the coefficients, coefficient in k, I mean it's a small norm, then you get exactly the action on this segment is not going to change. And so the Julia set will remain exactly the same. So in fact, in the parameter space of rational map over k, you have like some open set of rational map that satisfy this. So it's not
Into any kind of like measure of classification, you know, when
So
so sets have the same measure in the positive entropy case, even outside
So
of
you have rigidity. The map is very special, but it's not like over the complex where the coefficients are equally constrained. It's
So you say that the lattice map is a stable parameter, it's a factor.
Yeah, well, it's stable. Yeah. Okay, so for the next program on holomorphic dynamics, I'm going to discuss with Jan the perturbation or the generation of rational map over K, but this is not for today, neither for tomorrow. No, it's yeah, it's quite complicated. Okay, so I have 5 minutes to prove this result. Let's sketch the proof.
Can you explain a little bit more, or maybe after the Schroeder?
What do you want me to explain? Why this is I didn't say why. Okay, sorry. Yeah. So here the thing is that all multipliers, complex multipliers are constant, equal to delta. Here is not. Most of them are equal to delta. At least some of them, like map the image of torsion points. They are say 2 torsion points on delta square, but all other are constant equal to delta. So in this family, all multipliers are constant. So when you degenerate, what you're going to see is that your non-Archimedean map satisfies condition 3. Oh, and so it implies this, but you can also this directly. Okay. So, but here you have to understand what is the Berkovich identification of your family of elliptic curve. When it degenerates, you see a circle. And the map on this circle is going to be multiplication by delta, I guess. And so when you get to, you take the quotient at the non-Archimedean level and you crushing your circle to a segment, and the map becomes with like this piecewise linear. Okay, I don't have time to discuss this in details, but okay. So now 2 minutes. Okay, so yeah, so what I must say, so this result is has been proved by Rivera, Letellier, and myself a while ago, and but this Yusheng Luo gave a very nice proof of 3 implies 1 and 2 also. A difference that so we have a more general theorem, blah, but with more characterization in terms of the Lyapunov exponent, but I'm not going to discuss this here. Okay, so what is the idea of 1 implies 2? So the key idea is that, so you have a segment somewhere, and you know that the measure, this equilibrium measure puts some positive mass on this segment. And what you want to conclude is that, in fact, the Julia set, there exists some other segment, let's say J, such that the Julia set is fully contained inside the segment. That's what you want to show. And so what you do is that you look at this, you define an equivalence relation and say that 2 points are identified if the mass of the geodesic joining X to Y is equal to 0. And then you consider the quotient of your tree by this equivalence relation. So you need to explore a little bit what are the equivalence classes of these kind of things. You show that they are all equivalence class is a tree, blah, blah, blah. And so this quotient retains the tree structure of your Berkovich space. And because of your assumption 1, this is not reduced to just 1 point. So it's not reduced to a point. And what you want to show is that, in fact, so the key is, if you want to prove this, is that T, the claim, is that T is a segment. Once you know that T is a segment, then you can lift T to a segment inside P1 over K, and then blah, and then you get what you want. Okay. So I'm not going the the key is to observe that. So you know that mu f is preserved by f, and more than this, that the pullback of mu f is equal to itself multiplied by d. And so this implies a lot of structure this implies that f descends to dynamics on T. So let me call it, so you have T1. And so, I don't know, maybe capital F. So it induces a continuous map. But also something it's quite nice is that this tree is much smaller than the Berkeley space, in the sense that you can define actually a distance between, two classes of points by saying that this is a measure of the segment joining them. And recall that the measure is a probability measure. And so for this distance, in fact, T turns out to be compact of length 1. So it's quite a small tree. So you want to show it's a segment, so you proceed by contradiction. You assume that it has a branch point somewhere. F is, so mu F is ergodic. So the dynamics here is quite complicated. So you can show that F is in fact also ergodic for what? Well, for the Hausdorff measure attached to this thing, for the length, if you want. And so you know that points are moving around densely. And so if you assume that you have a branch point, you use the dynamics, and it's going to imply that, in fact, you're going to see branch points everywhere, dense set. Then F is expanding here on the Becquerel space, and so you can also show that capital F is expanding, as some kind of expanding property. And so what you so you combine these expansion properties on T with the fact that you have a lot of branch points to see that it's not possible that the length is finite. So you get a contradiction. So then the actual proof is using Bezikovich, if you want. So if you have a tree of length 1, then at a very small scale, what you see is, in fact, your tree is a segment. And so if you play with the expansion, if you assume that you have a branch point like this contradicts this fact. Okay. Okay, I'm over time. What can I say? Yeah, well, okay, so no, but because, so I could, let me stop here. Sorry.
Thank you, Charles. Are there questions? Comments?
Sorry?
Give you a hint to continue.
No, but so the proof of law is really very nice, but it's in 1 minute. It's not really possible. You need to. Okay, 5 minutes now.
So maybe I can ask my question again. Yeah. So you have a family of elliptic curve having multiplication by 2 on it, and the limit elliptic curve is a model curve.
Yeah. So you see a circle, right? The dual graph is a circle.
Yes, this is the dual graph. I see the circle, but I see another circle.
You see another circle. What did you take this morning?
Curve is multiplication by 2.
Yeah.
At the limit, it's P1 minus 1.25. We know the singularity, so it's the multiplicative group. And the limit is like z goes to z squared.
Yeah.
And so the unit circle is involved, and there I see periodic points.
Yeah.
Okay, so some of the periodic points see on the elliptic curve converge to this circle in one. And it looks like I constructed. It looks like I constructed classical points which are periodic. No?
Yeah. So this is exactly what we're doing tomorrow. Exactly. So you gave me an idea to have a new proof of Macmillan's rigidity result, and this is exactly what we're going to do. So we're going to look at the family, degenerate, find you're looking at the rescaling limit. So rescaling limit is monomial, then you have your circle, and then you're back to the family. This is exactly what we're going to do.
Saying that this rescaling limit, which has classical periodic point, is very different from the Berkovich dynamics, where you see no classical.
No, I see. No, come on. So if I have a rational, wait. If I have okay. So there are always classical points. You always have classical points, right?
Go out with the T, the infinity.
So what you see is that you have a point which is going to be fixed. This point is going to give you the sphere that you're where you have your rescaling limit, and then you have the set of directions. On the set of directions, this is a Riemann sphere. On the set of direction, your map is going to be z goes to a monomial map. Z goes z to the square. Okay, and so you have plenty of periodic points, which are endpoints here. So at the non-Acmean level, they are indifferent, but of course at the complex level, the multiplier is 2, so they are repelling. Okay, and so this is exactly this picture that you have to keep in mind. Yeah.
All right. Well, let's bounce again.